This lecture is an introduction to influence lines for indeterminate beams. Please review video SA18. It deals with moment influence lines for statically determinate beams, a good starting point for this discussion. Consider a simply supported beam. How do we qualitatively construct the moment influence line for a given point, like point C? As was mentioned in lecture SA18, we place a fictitious hinge at C, then draw the displaced shape of the beam due to a pair of bending moments placed at the hinge like this. Note that the diagram consists of straight lines only. What is the use of this influence line? It could help us figure out how to load the beam in order to produce maximum moment at C. For example, in the case of a series of concentrated loads, the diagram reveals the load location that produces the maximum moment at C. Let's pause here for a second and reflect on an interesting question. How does the shape of the influence line change if we change the location of point C? For example, if we move C to the left, what happens to the diagram? As point C moves, the fictitious hinge moves with it. Therefore, the vertex of the diagram moves with them as well. Note that here the entire diagram remains above the x-axis, regardless of the location of C. But as you are going to see in a minute, indeterminate beams could behave somewhat differently in this regard. Let's consider a beam fixed at the left end with a roller support at the right end. So the beam is indeterminate to the first degree. How do we construct the influence line for moment at C? Simple. We place a fictitious hinge at C, then draw the deformed shape of the beam as if a pair of moments were placed at the hinge, like this. Unlike determinate beams, here the influence line takes the shape of a curve in order to satisfy the boundary conditions. The two fictitious moments cause compression along the top fiber of the beam, meaning the curve is going to be concave up, both on the right side and the left side, but with the additional constraint that the slope of the curve at the fixed end would be 0. Suppose our beam is 10 meters in length and C is its midpoint. If the beam is going to be subjected to a distributed load of variable length, then what load position and length would produce the absolute maximum moment at C? The diagram tells us that when the load spans the entire length of the beam, where the influence line remains above the x-axis, then moment at C reaches its absolute maximum value. But indeterminate beams could pose a challenge when trying to identify the positive and negative regions under the influence line. To see how, let's observe what happens when we pick a different point for C. When we move point C toward the fixed support, the influence line changes shape and eventually a part of it drops below the x-axis. This happens naturally in order to maintain the slope and deflection constraints at the end of the two segments. Given such an influence line, then how do we determine the position and length of the distributed load that will cause the absolute maximum negative moment at C, for example? To do so, we need to be able to locate the point at which moment at C changes sign. That is, we need to know the exact location of this point so that we can determine the required length of the distributed load and its position on the beam for producing maximum negative moment at C. But this cannot be done qualitatively. We actually need to formulate a mathematical expression for the nonlinear influence line in order to determine its vanishing point. Let's see how that can be done. First, we are going to calculate the support reactions for the beam. Let L be the beam's length and NL be the position of the unit load for which we want to determine the support reactions. Note that N is a number between 0 and 1. We can analyze this beam using any of the techniques that we discussed previously. I am going to use the slope deflection method for this analysis. We denote the beam's end rotations as theta A and theta B, and the member end moments as MAB and MBA. They are assumed to act in the counterclockwise direction. The two slope deflection equations are Since the slope of the beam at the fixed end is 0, we can simplify the equations by setting theta A to 0. Also, the fixed end moments for the beam can be written as given that the counterclockwise direction is considered positive, then the slope deflection equations could be written this way. According to the slope deflection method, we need to write the moment equilibrium equation for each support point. So, the sum of the moments at B must be 0. Substituting this for MBA in the moment equation, we can solve this equation for theta B. Then, we substitute the result in the slope deflection equations to get the member end moments. Knowing that the sum of the moments at the fixed end must be 0, we can easily determine the moment reaction, MA, at the support. Having MA, now we can determine the remaining support reactions using the equilibrium equations. The vertical reactions are. So, here we have the support reactions in the beam as a function of the position of the unit load. This enables us to formulate a mathematical expression for moment at C in terms of N and L. I am going to define the position of C as M times L, where M is a number between 0 and 1. Because of the applied concentrated load, we end up with two moment equations. When the load is to the left of C, we get this equation. And when the load moves to the right of C, we have this equation. Having these equations, we can now determine where the influence line crosses the x-axis. This is the same as determining the value of N at which the moment at C becomes 0. Since M and N are between 0 and 1, then it should be clear that the first equation always gives us a positive value, since 3 minus N is always positive, and 1 minus M remains positive for all non-trivial M values. So, moment at C could be 0 only when N is greater than M, when this equation governs. To see when that happens, we set this expression equal to 0 and solve for N. Since we have a cubic equation here, we get 3 real roots, but only one of them gives us a value in 0 to 1 range. The valid root is. Still, to get a valid value for N, the expression under the square root must be greater than 0. This means either M has to be greater than 1 or less than 1 over 3. Since M cannot be greater than 1, then we can conclude that when M has a value less than 1 over 3, a part of the influence line drops below the x-axis. More specifically, when M is less than 1 over 3 and N is greater than the value given by this expression, then the moment at C is negative. Okay, let's wrap our minds around this using a couple of examples. Suppose our beam is 10 meters long and we want to draw the moment influence line for the midpoint of the beam. Here we are defining M to be 1/2. Since M is greater than 1 over 3, then according to the condition we just specified, the moment influence line is not going to drop below the x-axis regardless of the position of the unit load. Here are the two generic moment equations. Substituting 10 for L and 1 over 2 for M, we get. Now we can construct the influence line by graphing these equations. Note that at no point the diagram drops below the x-axis. However, if point C is located 2.5 meters from the left end of the beam, that is, if M equals 1 over 4, then the influence line ends up having a negative region since M is now less than 1 over 3. When we substitute 10 for L and 1 over 4 for M in the moment equations, we get. To construct the influence line for moment at C, we simply graph the two equations. To determine the point that the diagram crosses the x-axis, we need to evaluate this equation when m is 1 over 4. That gives us approximately 0.423 for n. This means the negative region of the diagram starts at 4.23 meters from the left end of the beam and ends at the right end of the beam. So, what would be the maximum negative moment at C due to a uniformly distributed load having a magnitude of, say, 23 kilonewtons per meter? It equals to the negative area under the influence line times the intensity of the load. How do we get the area? By integrating the moment equation with respect to n between 0.423 and 1. But since the moment equation is specified in 0 to 1 interval, we need to multiply the result by the length of the beam to get the correct area. Finally, we multiply the area by 23 to get the value of the absolute maximum negative moment at C. The moment influence line for any other point in the beam can be determined in a similar manner. As you can see, the qualitative approach for drawing influence lines may be of little use when dealing with indeterminate beams. In most cases, we need to approach such problems quantitatively. We will continue this discussion in future lectures.